Okay, so here we go with one of the major lessons in any high school geometry class, and it's on the Pythagorean theorem, and it's converse. And we have a little dialogue up here, which you can certainly read through when you get a chance. But I think most high school students are familiar with the rule long before they've ever proved it. I always like to see if I can prove something before I want to go and try to use it in general, though. So that's what we're going to do here. But certainly, those of you who are familiar with it, you're talking about when you have a right triangle and the legs of the right triangle, which are labeled as A and B in here, and the hypotenuse of that right triangle labeled as C, that if indeed it is a right triangle, then the length of this leg squared plus the length of this leg squared would equal the length of the hypotenuse squared. So A squared plus B squared equals C squared. The key thing there was the C squared, of course, is going to have to be the hypotenuse length. So what I've done is I've dropped an altitude here from the vertex, which is the right angle, down perpendicularly. So I've divided the hypotenuse into two pieces. X and Y is labeled here. And from our work in the last section with geometric means, we realized that what I've been calling the slanty side, or this leg over here, is the geometric mean between x, this portion of the hypotenuse that's closest to it, and the entire hypotenuse. So what I might want to do right off the bat is label this C as being literally just x plus y. It's this distance added to this distance. So we can think of that entire distance as x plus y. So since B is the geometric mean between x and C, I'm going to write that as B is the square root of the product of x and the entire length, which I'm going to call x plus y. So we have that relationship. Now, just to write that maybe more simply, we could say B squared is x times the quantity x plus y, or even distributing that x in, x squared plus xy. Now, similarly, we can do the same relationship over here with A being the geometric mean between y and its entire length of the hypotenuse, which again is x plus y. So we could say, all right, well, A is the geometric mean between y and the entire length, which is x plus y, or A squared is y times x plus y, or A squared is y times x plus y squared if you distribute the y in there. Now, one thing that we should remember from our studies in algebra is when you have the square of a binomial, let's say we have, I can use x plus y squared here. The common mistake is that students will say that that's x squared plus y squared. And of course I put a not equals because that's not true. What x plus y quantity squared really is, when you do the foiling, is you're going to get x squared on the outsides. The insides are going to be an xy, and the outsides are going to be an xy. And then of course your last term, y times y, is y squared. So we get x squared plus 2xy's plus y squareds. So if you recognize what we have here in A squared plus B squared, just adding those two together because we can, there's nothing that says we can't, we are going to have A squared, which is, I'm going to write y squared plus xy, yx is the same as xy, and then B squared, of course, is x squared plus xy, and then rearranging those terms, we have x squared plus 2xy's plus y squared, because we have like terms here and here. Now, interestingly enough, C is x plus y, so C squared is x plus y quantity squared, which of course is x squared plus 2xy plus y squared. So you can see that A squared plus B squared is exactly the same as C squared, because this quantity is what we just worked out right over here. So there it is. It's not it's not as dramatic as you might think it was. Pretty simple proof. If you're interested, there is a GeoGebra little exercise where you get to work with some shapes some right triangles, and it's a nice little exercise in seeing the Pythagorean theorem in action. So if you download the note sheet from chapter 8 in topics, you can look at that hyperlink. It'll be active, and you can check that out in GeoGebra. So of course, now that we have access to the Pythagorean theorem, tons of examples that you can work out with this, all fairly straightforward. But the one caution that we have is, as anytime you're doing one of these problems, you have to recognize which side is the hypotenuse, because that's the side that's going to be kind of flying solo. So in other words, we have a leg x squared plus 9 squared will have to be equal to 15 squared. And again, it's just important that 15 is the hypotenuse, has to be there. So we do the math, and we get x squared plus 81 equals 15 squared, which is 225. And so when you subtract 81 from both sides, we wind up with x squared equals 144. Now, that should be familiar that x is the square root of 144, which most of us recognize as 12. So this missing side length, of course, is 12. That was really nice in that it worked out that all three side lengths are integers, 9, 12, and 15. It can happen. We'll talk about that a little bit on the next page. Now we have an example here where we have some non-integers. We have some fractional values, and so we can do the same thing again, recognizing that 5/9 will be the hypotenuse. So we need to set up our equation that x squared plus 4/9 quantity squared is equal to 5/9 quantity squared. Of course, when you square a fraction, you square both the numerator and the denominator. So this will be 16/81, and this will be 25/81, and what we're left with is x squared plus 16/81 is 25/81. So when we subtract and we get 25/81 minus 16/81, we get 9/81, which you might recognize reduces to 1/9. So we have this x squared equals 1/9. So that means that x is the positive root of 1/9. And again, when you have a fraction underneath the radical, you can take the square root of the top and the square root of the bottom. We recognize the square root of 1 is 1, the square root of 9 is 3. So we get x equals 1/3. So again, kind of a convenient answer that we got there. It is a rational number. It's not an integer, but it's a rational number where both the numerator and the denominator are integers. So we have one more little challenging example here where we have a variable quantity for both of our legs. So we're just going to have to be careful with our algebra as we set this up, that the hypotenuse, of course, is 10. So we're going to let him be solo on that side. And we're going to have x squared plus the quantity x plus 2 squared is equal to 10 squared. And we'll see what this looks like. X squared. Now, again, as we FOIL this, we just talked about this on the other page, you're going to get the first term. I'm going to call x as my first term and 2 as my second term. You're going to get the first term squared. This middle term is going to be the product of 2 times x doubled, so 2x times 2, which is 4x. And the last term is going to be 2 squared, which is 4. And we get that, and that's got to be equal to 10 squared, which is 100. So now, grouping our like terms, we have 2x squared plus 4x plus 4 equals 100. Now, one thing we should know about quadratic equations when we have a squared term in them is we want to set them equal to 0 and see if we can factor them. So I'm going to subtract 100 from both sides, and I'm going to get 2x squared plus 4x minus 96 is equal to 0. And now the benefit of that is everything's got a factor of 2 in it, so I can divide everything, both sides, by 2 and get x squared plus 2x minus 48 is equal to 0. So if we take x squared plus 2x minus 48 and let it equal to 0, we're going to set it equal to 0 rather. We'll look and see if we can factor that. We're going to have x and x, and we're looking for two integers that have a product of negative 48 and a sum of 2. And it looks like it's going to be 8 and 6, specifically positive 8 and negative 6. So we get two solutions, x plus 8 equals 0, which leads x equals negative 8, and x minus 6 equals 0, which leads us x equals 6. Now, in the context of this problem, where we have x being a side length right here, we cannot have a negative value, so we toss that one out as extraneous, and we settle on x equals 6. So to just check this out, it turns out that if x is 6, then x plus 2 would be 8, and this would be 10, and sure enough, 6 squared plus 8 squared, which is equal to 36 plus 64, does indeed equal 100, which is 10 squared, so it checks out. Now, one of the cool spin-offs of the Pythagorean theorem is the concept of a Pythagorean triple. And a Pythagorean triple is a set of three integers that satisfy the relationship, the Pythagorean relationship that a squared plus b squared equals c squared. We've already seen this pop up a couple of times in our examples already. For example, the most common Pythag triple is 3, 4, 5. And we saw it pop up earlier that 3 squared plus 4 squared does indeed equal 5 squared. 3 squared is 9, 4 squared is 16, and 9 plus 16 is 25, which is 5 squared. So there's tons of these things out there. But as far as standardized testing goes, both SAT and ACT will frequently use problems that involve the Pythagorean theorem, and they'll incorporate Pythagorean triples. So if you're aware of these, it's like cheating on those tests in that you can kind of speed through them without having to do the arithmetic if you know these things are true. So for example, we see this collection of Pythagorean triples, and you can, if you don't believe me, go ahead and try it. 9 squared plus 40 squared, you will find that it equals 41 squared. I will be honest, these first four that they use, or that you see here, are used most frequently, and I'll say of those four, these first two are used the most. But the interesting thing about Pythagorean triples is that, but due to the nature of the proportions that exist in right triangles, multiples of Pythagorean triples also work. So in other words, what I'm saying is if you double everything in this first Pythag triple 3, 4, 5 and make it 6, 8, 10, that is also a Pythagorean triple. If you were to triple everything, take 3 times 3, which is 9, 4 times 3, which is 12, and 5 times 3, which is 15, you might recognize that one from the very first problem that we did, 9, 12, 15. You can do it, multiply by anything you want. Multiply by 10, 30, 40, and 50 is a Pythag triple. 30 squared plus 40 squared will indeed get you 50 squared. So when you take a look at these things, and take the 8, 15, 17 one, and let's say you triple it, so you'd have 24, 8 times 3 is 24, 15 times 3 is 45, and 17 times 3 is 51. So 24, 45, 51 might not jump off the paper even to an experienced mathematician as a Pythagorean triple, but if you just take a look at these things and say, okay, do these numbers have a common factor? And if they do, like they do in this case being 3, if you divide that common factor out and see that it's 8, 15, 17, you'll know that's a Pythagorean triple. So this example 4 here it says problems 1 through 5. There's only 4 of them listed here. They are just using multiples of the 3, 4, 5, this 5, 12, 13, the 7, 24, 25, and 8, 15, 17. So I'm going to leave you guys to do those on your own, where they're in each example, they're leaving you with one question mark. For example, I'll pick on this one right here because I know he's a little bit interesting. Number 1D. It's saying 1 1/3 is one side length, and then down here is 1, so that's the shortest side, and then it has a question mark here. So what I want you to realize is that looks awfully, you're like, how the heck is this a 3, 4, 5? Well, if you think about it, 1 is 3/3, and 1 1/3 is 4/3, and then you can see, oh, I see the pattern, 3/3, 4/3, 5/3. That means the last side must be 5/3. So that question mark would be 5/3. So that's going to be part of your assignment, is to go through each of these and determine what the missing side length is using the given Pythagorean triple. And again, these can be pretty easy if you find the common factor between the numbers that are given. For example, in this one right here, number 3, which is it's a 7, 24, 25, you realize 14 is 2 times 7, and 50 is 2 times 25. So you can see that you've got the 7 and the 25. So what we need over here is the 24, but it's got to have that same factor. It's got to be multiplied by 2. So, of course, 2 times 24 would be 48. So that missing side length there would be 48. Do a few of those, and it's nice if you can do them without your calculator by just recognizing the patterns that exist, because it'll go a long way in burning them into your brain. All right, so our last thought on the Pythagorean theorem is a couple of things. One, don't go assuming that every triangle that you see now is a right triangle and you can use the Pythagorean theorem on it. Pythagorean theorem is very particular to only working, it's a relationship that's only true in right triangles. Once you've said that, they go, well, is the converse then true? That if you have a situation where a squared plus b squared equals c squared, could you then determine that the triangle is indeed a right triangle? And you can, and that's the converse of the Pythagorean theorem. So if we see a triangle and we're wondering whether it's a right triangle or not, you can check, does the sum of the squares of the two shorter sides equal the square of the longest side? And if they do, the triangle is a right triangle. In addition to that, you can kind of pile on and say, hey, if the sum of the squares of the two acute sides is greater than the third side squared, then you know that that triangle is acute. And if the sum of the squares of the two shorter sides is less than the third side squared, then the triangle's obtuse. So you can kind of think about that and how it might work. Think about our basic 3, 4, 5 as an example. 3, 4, 5, which we know to be a Pythag triple, so we know that that's a right triangle. If you make this 5 guy a little shorter, let's make him 4.8 or something like that. Think about taking a little piece off there. That triangle is going to have to kind of scrunch down just a little bit with this 3 and this 4 to clamp down on that 4.8 that's there instead of the 5. So this idea should be fairly straightforward, that what's going to make an acute triangle is when this third side, the longest side, isn't long enough. In other words, it's not equal to the sum of the squares of the other two sides when it's squared. And similarly, if we tried to use 3 and 4, and instead of putting a 5 there, we put something like a 6 there. So you had a 3 here and a 4 here, and we would have to take those guys and open them up a little bit bigger than a right angle right there to fit that side length of 6 in. Okay, so for our last couple of examples here, we've got this triangle that's set up here with 6 and 8, and this angle measure is just listed as 1. And the questions right off the bat, the first one has nothing to do with Pythag. It just says what values of x would be reasonable to generate a triangle here. And we learned earlier in the year that the sum of any two sides of a triangle have to be greater than the third side. And there's kind of a long way to do this and a short way to do this. And the short way that we talked about after a little bit of exploration on it was that if you take the difference of those two sides, 8 minus 6, which is 2, and you take the sum of those two sides, 8 plus 6, which is 14, those are the values that x can be in order to form a legitimate triangle that would have three sides that would actually work together. And you kind of see why that works, because if you pick something that's, let's say, less than 2, like 1, you would have a 6 and a 1 and an 8. If you had a side that was 6 and a side that was 1, when you stretch them all the way out, the 6 there, and then make it a 180-degree angle, make that a 1 here, and you tried to fit an 8 on this side, it's not going to work. It's going to be too long. So that's kind of why that stuff works. But anyway, that's the shortcut to determine what is the range of values that'll get you a triangle when you're given two sides of a triangle and you're missing the third. So the small range would be the small end of the range would be the difference between the two sides, and the large end of the range is the sum of the two sides. So basically, the question 2 here asks us what values of x don't make a triangle. Well, we'd have to be values between 0, smaller than 2, and I guess you couldn't have a negative side, so we just need to think about a value that would be smaller than 2 and greater than 0. You certainly could not have a triangle that was in there, or if x was greater than 14, then it would be too long and you wouldn't be able to get a triangle. That third side would be too long. Now, in order to make it a right triangle, we'd have to say, because couple of things here. The obvious thing is, because of the way it's drawn, that you could say, okay, well, 6 squared plus 8 squared would have to equal x squared. And I don't know if you recognize it, but that's the 3, 4, 5 triangle, because doubled. And if you do that math, you're going to find out that x equals 10. And that's kind of like the sucker answer to this problem. It's not wrong, but it's just a little bit incomplete. We cannot be fooled by the picture here and assume that x is the largest side. What we know, though, is that 8 could potentially be the largest side since he's larger than 6. So if we had a triangle that looked like this, where x was here and 6 was here, and there was a right angle there, and 8 was going to be our longest side, then we'd have to say x squared plus 6 squared would equal 8 squared. So if we do that math, x squared plus 6 squared is equal to 8 squared. We get x squared plus 36 is equal to 64. So x squared is 64 minus 36, which is 28. And x would be the square root of 28, which is the square root of 7 times 4, which is 2 times the square root of 7. So the other solution to this is x could be 2 root 7. So you have to be careful on those to not just assume that the missing side is going to be the longest side. We know that we know that 6 couldn't be the longest side because it's not even longer than 8, though. So 6 will either be the shortest side or it will be the medium length side. What values of x would make it an acute triangle? Well, we could have a situation where we were going to play the game where x could potentially be the hypotenuse, if you will, the longest side. It's not really a hypotenuse unless it's a right triangle. So we could look at that situation. And for that, we could kind of do just what we did before and say 6 squared plus 8 squared would have to be greater than x squared. And of course, that's 100. It would have to be greater than x squared, which means x would have to be less than 10. Now, that's, again, part of our situation there where we're assuming that x is going to be the largest side. But now when we consider this situation where x could be the shortest side in this triangle, we found that 2 root 7 would make it a right triangle here. So if this side being 2 root 7 got a little bit longer, that would make this hypotenuse, if you will, the 8, be not long enough to do the job. So if x were greater than 2 root 7, so what we're really talking about, that would also be an acute situation. So basically what we're talking about is values between 2 root 7 and 10 would be the ones that would make this thing be an obtuse triangle. And make this thing be an acute triangle. And then what's going to make it obtuse is basically everything else. If you think about our potential here from what we found up in example 1, or part 1 of this example, number 5. 2 was our very smallest you could get. 14 was the largest. And we just found out that between 2 root 7 and 10, this is where we're going to be acute. At these two values, this is where we're going to be right. So that leaves obtuse being in between those two things. So to answer this question, we could be between 2 and 2 root 7, and also, or in between 10 and 14. So those are the range of values that would make this thing be obtuse. Now, if you got a little lost going through those last two situations that could make it acute or obtuse, I don't want you to get too freaked out by that. But what you might want to do to just kind of convince yourself is try a value in between these two as your x, like 2 root 7, the square root, we got that from being the square root of 28. Find a value that's in between there and 10, and then plug it in there and see what you get. See what happens when you test it in the acute obtuse test up here. And then lastly, maybe test ranges in between, any number in between these two. For example, like you could test 3 and 12 really easily as values for x here to show that it's going to wind up giving you an obtuse triangle. Now, what I'd kind of like you to think about as part of your homework is example 6, where it says any two right triangles with the same hypotenuse have the same area. And they're asking you whether this is true or false. So we haven't formally talked about area of triangles yet, but if you have a right triangle, if you think about it, it might look like that, where we have 3 and 4 and 5. And remember the area of a triangle, which I'm sure you did learn in middle school, it's 1/2 the base times the height. So you could consider a situation like that. And its area would be 1/2 of 3 times 4, which is 6. So the area of that triangle is 6. What this question is posing, though, if you have two triangles that have the same hypotenuse, if you've had some other right triangle that had a hypotenuse of 5, would it have the same area? And you could think about this and either try to prove it to be true, or you could use a counterexample using legitimate sides that would fit the Pythagorean relationship that would contradict this. So what I want you to do as part of your homework is to come up with an answer for that, true or false. True, you got to prove it to be true for all values. False, all you have to do is provide a counterexample. And then lastly, we also have some other homework problems here from your text, which will just give you some practice in essentially solving for missing sides of a triangle or determining whether a triangle is obtuse or acute or right using the relationships found up here. There you go.